We're going to talk about pizza some more. So there's our pizza recipe. If we have 4 crusts, 10 cups of cheese, and 15 ounces of tomato sauce, how many pizzas can we make? Depends on which one runs out first, right? So you can kind of think about this for a while. What number did you come up with? 3. 3 actually is the correct answer. But let's write it out and see what the process is. So what we want to do is we want to take each ingredient and find out how many pizzas that ingredient could make. This is not necessarily the fastest way to do it, but it works every time, and I think that's pretty good. So 4 crusts. Oh, I guess I'm using orange now. So 4 crusts, if we're trying to convert that into pizzas, we're going to multiply by the number of pizzas, divide by the number of crusts, and the unit crust cancels out. Our recipe tells us that we need 1 crust for every 1 pizza. So 1 pizza from every 1 crust. So if we use up all the crusts, we could make 4 pizzas. We can only make 4 pizzas, though, if we have enough of the other stuff. So next it said 10 cups of cheese. Well, we already did that one. So I'll do it kind of quick here. We get 1 pizza for every 2 cups of cheese. And we found that with 10 cups of cheese, we could make 5 pizzas. Can we actually make 5 pizzas, though? No, because we only have enough crust for 4. It's hard to make pizza without crust. It ends up just being melted cheese burning in your oven. The other ingredient is the tomato sauce. So 15 ounces of sauce. The ratio is 1 pizza requires 5 ounces of sauce. So you do that and you end up with 3 pizzas. So this is real life stuff. We can imagine this happening. You make 1 pizza, you make 2 pizzas, you make 3 pizzas, you go to make the 4th, you've got the crust and there's no sauce. You can't make the pizza. You can't make part of the pizza. You don't have sauce, okay? So how many pizzas can we make? 3. So the process here is I took each of my reactants, my starting ingredients, and I figured out how much product can I make if I use it all up, if I use that ingredient up, if I use the other ingredient up. And then I'm going to look at my results and I'm going to pick the smallest one. Because when I get to the smallest one, I run out of this ingredient and production stops. Does that make sense? So here it is in pictures. The person they hired to do this draws a lot better than I do. That's why they get paid for it and I don't. Okay, so the sauce is the limiting reactant. We can only make 3 pizzas. So we call this the limiting reactant or the limiting ingredient because it limits how much product we can make. What happens with the extra cheese and the extra crust? They're in excess. They're just going to sit there, right? Maybe we can save them and use them at another time when we get more sauce, right? Nothing happens to them. They just sit there unreacted, uncooked, unused. So the tomato sauce is the limiting reactant, sometimes called the limiting reagent. The maximum number of pizzas that we can make is called the theoretical yield. So in this example, 3 pizzas is the theoretical yield. If you have enough ingredients to make 3 pizzas, are you guaranteed to get 3 acceptable pizzas? Does chaos ever happen in your kitchen when you're baking? Never? Happens in mine. What if you dropped one of the pizzas? What if you got distracted playing League of Legends and didn't hear the timer and you burned one of them? Would you have 3 pizzas? No. So even though you had enough stuff and the reaction was happening, you don't always get what you think you can. So the theoretical yield is how much you could get if everything works perfectly. And that is the amount based on how much of the limiting reactant you have. So we talked about, well, what about the cheese and the crust? That is very typical of cooking, right? Where you have extras of most of the things. Like if you go to make cupcakes for your kid's birthday because they want to take cupcakes to school, right? You're probably limited by the number of cake mixes you have. You probably have more than the required 2 eggs and 1/3 cup of oil, right? It's very unusual for you to have just the right amounts of everything. And in chemical reactions, it's also unusual to have just the right amounts of everything. Usually there's one thing that limits the reaction and the rest of the stuff just hangs out. It's excess. Those are the excess reactants. So the actual amount of product is called the actual yield. So if you burned a pizza, you dropped one on the floor, the cat got up and sat on it or something, then you've only got 2 pizzas. That's how much you actually made. You could have made 3, but something screwed up, you know. So we can use percent yield to express how efficient the process was. So percent follows the pattern of the part over the whole. So the part is the amount you actually made out of the amount that you theoretically could have made if everything went perfectly. And then you multiply by 100 to get a percentage. So that's percent yield. This is a summary slide. These are terms that you need to know. Limiting reactant, the reactant in excess, the theoretical yield, the actual yield, the percent yield. So let's apply these concepts to a chemical reaction. We're going to go back to the combustion of methane, which we looked at when we were learning how to balance equations. So here's a balanced chemical equation, and here are space-filling models of these. So we need, for every 1 molecule of this methane, we need 2 molecules of oxygen in order for the reaction to proceed. If we only had 1 molecule of oxygen, nothing would happen. We can't have half of a molecule react. So if we have 5 molecules of methane and 8 molecules of oxygen, what are we going to end up with? Well, we're going to look at each of the reactants first. So here's the methane. There are 5 methane molecules. From our equation here, we see that we are going to generate 1 carbon dioxide molecule from every methane molecule. So if we had 5 of these, we could make 5 of those. It's a little bit like the crusts and the pizzas. If we have 8 molecules of 8 molecules of oxygen. So here's our 8 oxygen molecules. The equation tells us we're going to make 4 molecules of CO2. 1 molecule of CO2 for every 2 oxygen molecules. That ends up being 4. I should bring the equation onto this slide. For every 2 of these, I get 1 of those. That's where that ratio is coming from. So there's my oxygen. I have 8 of those. I get 1 CO2 for every 2 oxygens, and so this gives me an amount of product. So if all the methane reacted, I could make 5 molecules of CO2. If all the oxygen reacts, I can make 4 molecules of CO2. Whichever is smaller is your theoretical yield. 4 is smaller than 5, so the theoretical yield is 4 molecules of CO2. Now the question was, what is the limiting reactant? Well, once you determine what your theoretical yield is, the smallest one, go back and look at what reactant gave you the smallest number. Here it was the oxygen. So in this example, oxygen is the limiting reactant. Any questions? So now we're going to apply that to chemical equations using masses and moles, and it can get a little confusing. You can lose sight of the big picture. This is how your book explains to do it, and it is correct. It's just not the way I like to do it. So they say, well, you've got a mass of A and a mass of B. So calculate mass of A to moles of P, the product, and then just hang out there. Take mass of B, go to moles of B, moles of product, and stop. And ask yourself, which is smaller? Take the smaller one and then calculate the mass of product. That is fine. That's a very nice way to do it. I'm going to show you what I like to do. So I'm going to just white that out there. Yeah, I guess orange would be good here. So just continue on here. So from moles of product, go to grams of product. And from that moles of product, go to grams of product. And now ask yourself, which is smaller? And that's your answer. It's the same calculations, but I think this method involves less thinking. You just string it all together and be done with it. So this is the method I'm going to use. Ammonia can be synthesized by this reaction. What is the theoretical yield of ammonia in kilograms that we can synthesize from 5.22 kilograms of hydrogen and 31.5 kilograms of nitrogen? So again, I am going to take my numbers and write them under my chemical equation. So 5.22 kilograms of hydrogen. So I'm going to write 5.22 kilograms under hydrogen. And 31.5 kilograms of nitrogen. The question, what is the theoretical yield of ammonia? So question mark here, and it's requesting kilograms. Well, this has a title on it, limiting reactant, so that kind of alerts us, hey, this is a limiting reactant problem. On an exam, there aren't any titles on the questions. So how do you recognize this as a limiting reactant problem? I have 2 reactants and I have 2 masses. If it's not a limiting reactant problem, you'll only be given 1 mass. But here I'm given 2. So I have two reactants and I have a mass for each. I don't know which is going to run out first. You can't just go by which has the lower mass. I'm going to do 2 calculations. They are very similar to each other. So I'm going to go grams to moles to grams for the hydrogen and grams to moles to grams for the nitrogen. Now, did you like the putting K on the side and leaving it, or do you want to see the whole thing? Nobody has an opinion. Okay. I'll just make it up as I go along. Okay. 5.22 kilograms of hydrogen. So this time I'm going to do the unit conversions, at least for one of them. So 5.22 kilograms of hydrogen, I need to convert that to grams of hydrogen, because that's where our path starts, grams to moles to grams. So I've got grams, and now I'm going to go to moles of hydrogen, and I'm going to divide by grams of hydrogen so the units cancel out. And then I'm going to go to moles of what I'm trying to find, which is moles of ammonia. And I'm going to divide by that previous term. It's not a nitrogen, it's a hydrogen. moles of H2. And then I'm going to go here, grams of ammonia dividing by moles of ammonia. And then what do I need to do? It's asking for kilograms. So I need to convert to kilograms at the end. Any questions? This is the regular grams to moles to grams with a slight variation. I'm going to kilograms on the end and I'm starting with kilograms on the beginning. So here's this conversion. Kilo means 10 to the 3. So I'm going to put 10 to the 3 where the kilo is not. So 10 to the 3rd grams is a kilogram. Here I need the molar mass of hydrogen. Hydrogen is a diatomic element, so it's H2. So that's 2 times 1.008 or 2.016. The middle is moles to moles, and there I get my numbers from the coefficients. 3 goes in front of H2, and 2 goes in front of ammonia. The next term would be the molar mass of ammonia. So you can calculate that. You'll come up with 17.034. And then we have this term. Again, kilo means 10 to the 3rd. So kilos on top, I'm going to put 10 to the 3rd where the kilo is not. Now, if we look, can you see that? It kind of shows up. I don't want it to be too bright. Do you see those two terms there? Here I have 10 to the 3rd on top. There I have 10 to the 3rd on the bottom. They cancel themselves out. Okay? That's why I could just set the K aside and go through with it like this. Okay, so let's do the math. 5.22 times 1 EE3 divided by 2.016 times 2 divided by 3 times 17.034 divided by 1 EE3 equals. Syntax error, great. What did I do? Times there we go. 29.4? Yeah. Thank you. There was a button that I thought I pushed that did not get pushed. I'm starting with 3 sig figs, so this is going to end with 3 sig figs. 29.4. Write down 2 extras. The unit is kilograms of ammonia. Okay? I need to do another very similar calculation. So I'm going to start with the other ingredient, the other reactant, 31.5. I'm going to do the kilo business the other way this time. So that many kilograms of NH2. And I made the kilo red because I'm not going to cancel it out. I'm going to just sort of put it aside, and I'm going to go grams to moles to moles to grams, and then the kilo will still be there. So I'm going to go to moles of N2, dividing by grams of N2, and that cancels the grams of N2, but not the kilo. And then I want to go to moles of NH3, And I'm going to divide by moles of N2. And then I'm going to go to grams of NH3, dividing by moles of NH3. This term and this term are exactly the same. So I'm still converting to grams of ammonia, and so that's the same. That's still the 17.034. In the middle, mole to mole ratio in front of nitrogen is nothing, so that's a 1, and in front of ammonia is a 2. So I get 2 moles of ammonia for every 1 mole of nitrogen. And then I need the molar mass of nitrogen, 2 times 14.01, 28.02. It's not an 8. 28.02. So 31.5 divided by 28.02 times 2 times 17.034. 38.299 kilograms of ammonia. Anybody else get that? Thank you. I'm not rounding these because I don't have a final answer yet. So what we're going to do is we're going to look at the two numbers we got and say, which one's smaller? Well, the 29 is smaller than the 38, right? This is the smaller one. So I'm going to take that value, round it correctly, 29.4 kilograms of ammonia, and that's the answer. What is the theoretical yield? It's not the actual yield. It's the theoretical yield. So the theoretical yield is calculated using stoichiometry. The actual yield is measured when you actually do the thing, right? You can't predict, well, they're going to screw up 1 pizza out of 10. What if they screw up 2? What if they don't screw up any, right? But you can calculate, based on the amount of ingredients, how many they could possibly make. What's the limiting reactant in this problem? It's hydrogen. So this is the smaller amount. So if I go back and look here, this is my limiting reactant. The limiting reactant is the reactant that gives you the smallest amount of product. Limiting reactant. Here's another one. Mining companies use this reaction to obtain iron from iron ore. The reaction of 167 grams of Fe2O3 with 85.8 grams of CO produces 72.3 grams of iron. Determine the limiting reactant, the theoretical yield, and the percent yield. The theoretical yield is always something you have to calculate. The actual yield will be given to you. The actual, okay? So what this is saying here is they took this amount of Fe2O3 and they reacted it with this, and it actually produces this much iron. So they did the reaction. They're telling us this is how much iron we got. That's the actual yield. So this right here is the actual yield. Let's take those other numbers and write them under their formulas. So 167 grams of that one and 85.8 grams of that one. They're asking us for the theoretical yield. The theoretical yield you calculate using stoichiometry. Here we have to do 2 calculations because we don't know which one of these is going to limit the reaction. and we're trying to find out how many grams of iron is formed. That's going to be the theoretical yield. And then remember that percent yield is going to be the actual divided by the theoretical times 100. So in our pizza example where we had 15 ounces of sauce, we figured out we can make 3 pizzas. Could our actual yield be greater than the theoretical yield? With correctly made pizzas? No, it's impossible, right? It's impossible. Because you used up all of one thing, the reaction stops. Now, things can go wrong, and it can appear that you have higher than 100% yield. But something has gone wrong. Like somebody didn't measure the sauce right, and they made more pizzas. They made 4 pizzas, but they didn't have enough sauce on them, or something else screwy happened. So we did that experiment with the copper, and a lot of you came up with, 70, 80, 90% recovery of the copper, and some people came up with 105%, right? That doesn't mean they made copper. It means that something went a little bit wrong, okay? So the actual yield should be smaller than the theoretical yield. And if you have a hard time identifying which is which, that's going to work most of the time. You got 2 yields, one you calculated, one that was given to you, put the small one on top. It'll work most of the time. So we need to have 2 calculations here to calculate our theoretical yield. We're going to start with the one reactant, and then we'll do the other reactant. Grams to moles to moles to grams. So 167 grams of Fe2O3. Grams to moles. So to moles of that, and then I'm going to go to moles of the other thing, and then I'm going to go to grams of my product. Grams to moles to moles to grams. Dimensional analysis, I'm just putting the previous unit in the denominator so those cancel out. And then those labels, those units tell me where to put my numbers. The mole ratio is from the coefficients. 1 mole of Fe2O3 will give me 2 moles of iron. So I'm going to get 2 moles of iron for every 1 mole of Fe2O3. This last one, the molar mass of iron, that's easy because that's an element. That's just 55.85. Read it off the periodic table. But Fe2O3 we're going to have to calculate. 2 times 55.85 plus 3 times 16. $159.7. So 1 mole of Fe2O3 weighs 159.7 grams. So start at the left, multiply by the top, divide by the bottom. So 167 divided by 159.7 times 2 times 55.85. I started with 3 significant figures, so my answer will have 3 significant figures, but I'm not at a final answer yet, so I'm going to write down 2 extra digits just to be safe. Then I'm going to take the other one, the CO, and I'm going to do a very similar calculation. So 85.8 grams of carbon monoxide. I'm going to convert that to moles of carbon monoxide. And then I'm going to convert that to moles of iron, and then to grams of iron. Grams to moles to moles to grams. Ending up at the same place. I'm not going from this to that. I want to find the mass of the product that I'm interested in. So grams of CO down there, moles of CO, moles of iron. Those cancel out. Mole ratio in the middle, 3 carbon monoxides for every 2 FEs. 3 carbon monoxides, 2 FEs. The last one is the same, 55.85. And then I need the molar mass of carbon monoxide, so 12.01 plus 16. I think that's 38.01. Now it's 28, right? Help me out here. 28? Yeah, so, go ahead and use your calculator for things like that. So 85.8 divided by 28.01 times 2 divided by 3 times 55.85 equals. Again, 3 significant figures, 0.05 grams of iron. Don't add these together, just pick the smaller. Because once I've made 114.05 grams of iron, I've used up all the carbon monoxide and I can't make any more iron. Doesn't matter how much more Fe2O3 is there, the reaction won't happen. So my theoretical yield is the smaller of these numbers. Here they're asking for what is the theoretical yield. So I'm going to take that, the smaller one, I'm going to now round that to the correct number of significant figures and say this is the theoretical yield. They also want to know what's the limiting reactant. This is the smaller number. It came from this reactant. So carbon monoxide is the limiting reactant. Carbon monoxide is the limiting reactant. And then they want the percent yield. It's challenging to fit all of this on one slide. Well, I've got my actual yield and I've got my theoretical yield. So here's my actual yield that was given to me. So my percent yield is the actual yield, 72.3 grams of iron, divided by the theoretical yield. I'm going to choose to use this unrounded one, just to avoid possible rounding errors. So 72.3 divided by 114.05 times 100. And that should have 3 significant figures. 63.393%, which I would round to 63.4% yield. Any questions? Yes? It's possible for the percent yield to be over 100, but that means that there's something wrong happening. Like you're not recording the measurements correctly, or you're doing the calculation wrong, your sample's wet, something like that. So it should.
The actual yield is
The actual yield is,
that we measure.
if you were doing the experiment, that's how much you actually get. The theoretical yield is in theory. So if we do a calculation on paper, we're not actually doing it, this is what we think we could have happen. So that's the theory. But actually, when we do it, we get this much. Okay? So in theory, from this amount of starting materials, in theory, the company could have gotten 114 grams of iron. But they only got 72.3. So they're thinking, we're wasting some stuff here. What can we do to increase our percent yield? We'll make more money that way. Now, it's not always possible to get even really close to 100%, because it's real. Real isn't perfect. Anybody else have any questions?